Good morning, everyone. So, thanks for coming on a beautiful Saturday morning. And first thing, we want to have a big thank you to Tony Pitts. So you've seen her outside a lot. So she's actually been organizing the Saturday Physics event for over 14 years. And So Tony, you want to come down? We actually have a flower for you.
So for those of you who are new to this, welcome. And you only get to see her once because she's leaving the university to pursue some exciting new endeavors. For those of you who've been around for a while and are coming back, you know Tony is just a mainstay here in the department and has been instrumental in many things. And I want to show you one other thing that maybe you're not aware of that she's quite well known for, and that's how she supports our students here at the university. Obviously, the work she's done on Saturday Physics over the last decade plus has just been amazing. This picture is Tony with Professor Ronald Bailey when she won the Campus Award for Diversity. And I want to just show you just a quick video. This will not take, let's see. I lost my cursor. There we go. This was the award video for her when she was presented with this award.
Well, Tony is the manager, basically, of the RU program, and that for more than a decade. And she has been doing a fantastic job.
She's a big help in getting us out there and connecting us with people that we probably wouldn't otherwise be talking to get into physics.
To work here and to know all the wonderful things that the scientists do, all of the discoveries that they make, all of the high-level research that they do, and to know that maybe those doors are not open or not as welcoming to other people who have something to bring to the table really made me sad.
Research has shown that diverse work environments and working groups are more creative, more successful than homogeneous groups.
Our program is now 70% women and 35% underrepresented minorities, and I'm really proud of that.
Tony is constantly inviting members of the department to come speak to incoming women in physics. So they'll come to her office and kind of learn about the physics department, and then we'll talk to them about how cool it is to be here, and she's always so welcoming.
Do you know, one young man came, and he was from an HBCU, and I asked him, why is it that nobody else from HBCUs applies to our program? Because I'd called people, I'd written letters, to department heads, faculty, and he said, nobody ever asked us. As soon as I could, I went to visit Alabama A&M. And the next year I had 2 kids from Alabama A&M apply and come to our program, which was really wonderful.
And Tony is a mentor that's available for students from underrepresented groups, making sure that they can find support if there are difficulties. And Tony does a fantastic job over many years in doing exactly this.
For her dedication to recruiting underrepresented students in physics and her outstanding mentorship and advocacy that helps them succeed, Tony Pitts is a 2016 recipient of the Lorene Y. Cowan Make a Difference Award for Leadership in Diversity.
One of the best parts about doing Saturday Physics every year is seeing all of you come back. And I don't always remember your name, but I always recognize your face. And it's just really nice to know that there's a community of people here who love science. And I hope that you will, when you go to talks like this, tell young people so that they can be excited about science as well. And please keep coming to this program. And I I also want to say just one more thing. My biggest job when I leave here is going to be taking care of this big guy. And on October 18th, we will have been married 20 years.
Okay, thanks, Tony. So back to the main programs. In 2 weeks, Professor Matthias Perdikan will talk about nuclear proliferation, a very timely topic. And it's a pleasure to introduce today's speaker, Professor Kevin Pitts. Professor Pitts got his PhD at the University of Oregon in 1999. Then he, after a few years working at Fermilab, he joined the department. He's been here since he's been here since 1999, so many years. And so he continues to do research at the Energy Frontier at Fermilab on CDF and G-2. He also has passion and talent for teaching. And so he's won many awards for research and teaching. He now is the vice provost for undergraduate education. So let's welcome Professor Pitts.
Thanks very much, Liang. I really appreciate it. As Liang mentioned, so first of all, in case you didn't figure that out, Tony and I are married. It's been we collaborated for quite some time on Saturday Physics, and Liang took over, which has been great. This has been just an amazing program. Inga's here. Many of you know Inga. Inga's been involved in this program basically since its inception, and it's just it's really great to see this continue and be such a great venue. It's really fun for me to be here and to talk about something that I think is interesting and a topic that has a lot of real life applications, and hopefully we'll have a little bit of fun today as well. Before we get started, you can see we have some demonstrations up here, and we have some folks who are instrumental in making these instruments all happen. Erica Smith is right here. Erica's just an amazing person in all that she does to help not only with Saturday Physics, which is kind of a side thing, but what we're doing here in the classroom on Monday through Friday, which is doing some really amazing things and educating young people in science and technology. And so Erica and her team, Hannah and Sonia, were here early this morning setting things up and helping me out and helping to make sure that I don't injure myself or irradiate myself or anything like that. And so thank you very much, all of you, for the work you've done. The other thing I want to say is that, as Liang said, I'm vice provost, which means I spend a fair amount of my time now as an administrator. So it's really fun for me, first of all, to think and talk about science every now and then. But on Monday through Friday, I have to wear a coat and tie to work. So I was dying to, be on Saturday to be able to wear shorts and a polo. So if I'm underdressed, you can at least see why. So I want to talk about radiation today, and I have to admit this is a little bit intimidating because a few of the folks, actually probably more than a few of the folks out here in the audience, probably have more expertise than I do. So feel free to ask questions or make comments or add to the discussion along the way. I want to talk a little bit about the science, but I also want to talk about some of the applications and relevance. That's really the goal here. And I think it was just good fortune that Professor Matthias Gross-Perdikamp, he was actually in the video about Tony, that's Matthias, is talking in 2 weeks. And he's going to talk about some things related to kind of nuclear weapons, nuclear proliferation, things like that. So it's really great that we kind of aligned the talks like this. Like I said, probably accidental. Most good things we do here are accidental. But then once we do it once, we take credit for it and move on. So anyway, like I said, please feel free to ask questions or add comments along the way. Not a problem at all. I want to talk a little bit about what radiation is. There are different types of radiation. You can probably imagine from the title, it's already very suggestive. Radiation, friend or foe? And the answer is, well, it depends, or yes, both. That's what we're going to see today. We'll talk a little bit about where we encounter radiation, how we define it, how it can affect us, both in good and bad ways, which is really important. And then at the end, I'll actually point out some other applications for radiation that you might not have been aware of. Okay, so let me start with a question. I'm not going to ask you to raise your hand on this one, but I do want you to think about it for just a second. Would you eat food that has been irradiated? Okay, I have some hands going up, so all of you get a minus because I said we're not raising hands. Listens and follows directions. No, it's completely fine. And of course, we're going to talk about this a little bit more. I think the answer is it depends. It depends on the kind of radiation and how the food was irradiated. In most cases, the answer is probably not a problem. And we'll talk about that in just a minute. Here's a different question. What's scary about radiation? This one I will let. Does anybody want to answer? Take a shot at this one. Kills cells? Alters your DNA? See, you guys know. All right. Pardon me? A Godzilla, okay. Yes? Can't see or feel it, right? We're actually swimming in radiation right now. Not a lot, but we're swimming in radiation right now, and you can't feel it. Ow, ow, ow. Doesn't work that way. Very good. Others? Burns tissue, okay. Actually, I think we should just... hard to measure, hard to quantify? Kills rapidly dividing cells. This is an incredibly knowledgeable audience. I think we just wrap up and call it a day. Yeah, so you could be getting, so one of the things we think about is a really good point. So one of the things we think about, you get a lot of radiation, maybe your hair falls out, maybe you have a radiation sickness, but maybe with lower levels of radiation, maybe you don't even see the effects for decades, right? For example. Cumulative, okay, great. Science can be evil. Well, here are a couple of examples of that. Radiation can turn you into a shrinking man or an amazing colossal. So radiation can both shrink and apparently expand. Interesting thing about this, because I remembered these movies. So the shrinking man, he got radiation, but it was combined with some kind of fertilizer. That was what made him shrink. The other thing that was interesting about this when I pulled it down, both of these movies came from 1957. Same year. Interesting. Anyway, so radiation can do all kinds of things, and neither one of these things are real, but it's kind of what makes it scary. Let me give you a definition of radiation. I'm not going to get terribly technical today, but I want to try to point out a couple of the highlights and use this to help explain a little bit about the different types of radiation. So first of all, let me just start with this definition. Radiation is the emission of energy as electromagnetic waves or as moving subatomic particles, especially high-energy particles that cause ionization. Now, there's a lot there. I want to unpack it just a little bit. So the first thing is emission of energy, okay? That means radiation carries energy. And here we're talking kind of about the energy related to motion. And we all have a sense of what's a lot of energy and what's a little bit of energy just from everyday life. And my simple example here is, I think everybody would agree that a car moving at 60 miles an hour carries more energy than a car moving at 5 miles an hour. Okay? So energy associated with motion. Faster you're moving, the more energy you're carrying. Now, of course, with radiation, we're not talking about cars, we're talking about very tiny particles, and I'll talk about that in a few minutes. But that's one of the things that kind of is relevant. The other thing that's relevant is how massive the object is. So which carries more energy, a car traveling at 60 miles an hour or a loaded semi or a school bus traveling at 60 miles an hour? And the answer is the school bus does, because it's much more massive. So it's got a lot more mass moving at 60 miles an hour, so it's more energetic. So radiation carries energy, and that's very important. Someone mentioned earlier about how DNA can be damaged by radiation, and it has to do with the energy that carries radiation. If the radiation you're exposed to doesn't have enough energy, then it can't damage your DNA. So it depends on the type of radiation. What's next? Electromagnetic waves or as moving subatomic particles. So there are different types of radiation, and I want to talk about that in just a couple of minutes. And then the third thing is especially high-energy particles that cause ionization. So high-energy radiation causes ionization, and we're going to come back to that, but that's where we get into a lot of the effects related to potentially, for example, on humans at least, DNA damage, which may lead to cancer, birth defects, or other kinds of radiation sickness. So we're going to come back around to that. But I want to start with this whole thing about electromagnetic waves, because this is really interesting, I think. And by the way, when I say something's really interesting, my daughter says that means he's going to say something that's annoying and boring. So your mileage may vary, okay? The electromagnetic spectrum. Electromagnetic waves, we're swimming in electromagnetic waves right now. Light, visible light, is coming from the lights in the ceiling. We'll take a look at infrared radiation in just a couple of minutes. There's wireless internet in here, so there's Wi-Fi swimming around. Have any of you heard about this new thing, this brand new technology just came out? It's called a cell phone. Cell phone, and turns out you don't need a long wire to plug it in, right? Why is that? Because electromagnetic radiation is being received and sent from your phone. So the electromagnetic spectrum has a lot of components that are around us. Now, what are we looking at here? This is the electromagnetic spectrum, and these numbers here denote the frequency of the electromagnetic waves. And on the very left, it's low frequency, which means that the waves are going up and down very, very few times per second, okay? And that we should think of as low energy. So the left-hand side of the spectrum, I'm going to show it several times here over the next few minutes. This side is the very low energy side of the spectrum. So this is the car traveling at just a couple miles an hour. And as we go to the right, the car is speeding up. This is a higher energy part of the spectrum. This is the very high energy part of the spectrum. This is the car traveling at almost the speed of light, okay? So super energetic. Now, notice, as I go each one of these tick marks, notice that what changes here is the exponent. That means each one of these is getting 10 times bigger, okay? So for example, if I compare AM radio to shortwave, the shortwave frequency, and therefore energy, is actually 10 times bigger than the AM radio. So here we go. You know, if we go from here, 10, 100, 1,000, 10,000, a million, and then young people can keep counting, but I've run out of things to say when it comes to counting up by tens really quickly. So this is the low energy side of the spectrum, and this is the high energy side of the spectrum. Now, one of the things that is swimming around this room, which is actually on the lower energy side of the spectrum, is radio waves, AM and FM radio waves, okay? So I need a volunteer to help me show how radio waves work. Would you mind volunteering? Come on down. It's okay. If you want to later, I got a really cool one for Predator. All right. So let's see if we can turn the lights on here. Okay, so what's your name? Uma. I'm Kevin. Nice to meet you. So Uma's going to dance for us. Did you know that's what you signed up for?
Yes.
Okay. All right. So this is new technology that I need my glasses to see, but let's see. Oh, football pregame. There's got to be some music somewhere on the spectrum, doesn't there? All right, thank you. Thank you. Okay, so what's going on? So there's a transmitter around here somewhere, not in this room, right? It's somewhere, and I don't know what our station is, but it's not very far away, and it's transmitting FM radio waves out in all directions, which is really kind of not very efficient if you think about it, because it's going in all directions, but in fact, we really just want them right here. So that's why there are some changes going on in how we actually transfer information through, for example, satellites and things like that. But anyway, this antenna then receives the FM waves, which again are kind of on the lower energy side of the spectrum, and then gets converted to sound, and that's what we hear, okay? Now, what I'm going to ask Uma to do is get in this thing called a Faraday cage, and we're going to see what happens, okay? And I promise it's not electrified or anything like that, okay? All right, now it's really quiet in there, so when you get inside, I'm going to have to start yelling, okay?
Okay.
Okay, can you still hear me?
Yes.
You can still hear me?
Yes.
Okay, now I have to yell really loud. Can you hear me?
Yes.
Oh. Wait, what happened to the radio? It's quiet. So this Faraday cage is basically a copper mesh that's around her, and it's blocking the FM radio waves. Is it blocking visible light, which is another part of the spectrum? See over here further to the right where we got the little rainbow? Visible light's higher energy than FM rays. Is it blocking visible light? Can anybody see Uma? Yes. So the light's getting through. It's bouncing off of her, and it's bouncing back to your eye so you can see her, but it's blocking the radio waves. This is a form of radiation. It's not what you think about when you talk about nuclear power plants and atomic bombs, but it's a form of radiation, and it's bouncing around this room like crazy. And we're back to a commercial. Thank you, Uma. By the way, the whole sound thing was a total ruse. Sound waves are air molecules. They're not radiation like that. They're just air molecules bouncing around. The air molecules can pass right through. It's just a mesh. We can hear Uma the whole time. Yes, please. Where are submarines? That's a good question. I'm not sure about that. There's some really interesting science. Yes, that's right. And there's some really interesting science that has to do with how those waves will be transmitted through water, because water is a dense medium. But I don't know where they're at on the spectrum. That's a good question. They're certainly on the lower end, but I don't know where. Yeah. And actually, sound waves in water are actually also very interesting. The sound waves in this room are the air molecules bobbling around. That's not electromagnetic radiation. That's just air molecules bumping into each other. And in fact, there's some really interesting effects there in the atmosphere and also underwater, depending on what your depth is, because of the temperature and the pressure in the water. Different topic for a different day. Yes? Radar is radiation. Radar is on the kind of the microwave part of it. And so radar is sending out electromagnetic radiation. It's bouncing off of stuff and coming back. And so that's how radar was really developed during World War II. The technology's been refined like crazy, and we have a lot better radar now than we did then. But yes, that's part of the spectrum. I'm going to come back to kind of potential dangers with non-ionizing radiation. This radiation is called non-ionizing because it's not energetic enough. This stuff is called non-ionizing because it's not energetic enough to damage your DNA. Okay, so we're not worried about FM waves around the room or microwaves or radar, things like that. From the standpoint, they can't damage our. I'll show you a couple examples of this, but they can't damage our DNA. Yes. Yes, and I just got a little, yes, thank you for asking. I got a little bit ahead of myself because I'm going to talk about this in a minute. So when radiation can come in and knock electrons out of atoms, that's what we refer to as ionization. And I'm going to come back to that in a minute. And the point is there, if in that energy range, if it's energetic enough to knock electrons out of atoms, that means it's also energetic enough to break chemical bonds. And that's how DNA can get damaged. Yeah, thanks for raising that. I got ahead of myself. Please. Yeah, so I'm going to come back to that in just a second, okay? That's a great question. So, but what I want to show next is, so here's visible, okay? And of course, we're bathed in visible light, which is good because we can see each other. We can see the screen. Right next to the visible, on the low energy side, is infrared. And infrared radiation is really interesting because it is associated with heat radiation. And so I want to show you an example of infrared radiation. And may I have a volunteer? This one, no dancing involved, I promise. So let's see. So Erica, I go RGB, main menu. Oh, on video. Okay, thank you. Main menu. This is a quiz. Video routing and both. Thank you. 3 both. And I should turn off the lights. Oh, I'll do that over here. Okay. And what's your name? Maria? Thank you for coming down here. You're going to be on camera, okay? You're going to be on this camera right here. You know, I said there was no dancing, but you can dance if you want. Wave, Maria. Show everybody that that's you on camera. Very good. Now, what do we see there? What do we see? We can see Maria. It's kind of hard to see her face, isn't it? You can't see her features. You can see her nose a little bit. What else do you see on her face? Your glasses. Okay, and we can see her hair's a little bit darker. Okay, and then I'm going to come in and photobomb. So infrared radiation is actually associated with heat. So what we're seeing is we're seeing Maria's heat signature. Things radiate in the infrared part of the spectrum. This is one of the ways heat gets transferred. So of course, we're pretty warm, right? We're 98 degrees. Let me check. Yeah, 98. And so we're all radiating energy. This is quite common. And of course, this also, at the fast food place, they'll have the kind of what look like red lamps to keep the food warm. Well, part of that's visible, but the majority of that energy is actually in the infrared part of the spectrum. You can't see this with your naked eye. You need a special camera like this, infrared camera. Now, her glasses are dark. Now, around her eyes, she's radiating heat just like the rest of her face, but we're not seeing it because the infrared radiation doesn't pass through the glass very well. So on a let's say it's kind of a cool but sunny day, and the windows are up in your car and it's closed, and you open up the car door and you get inside, is it the same temperature as it is outside? No, it's much hotter. Why is that? The energy comes in from the sun in mostly the visible part of the spectrum. The inside of the car heats up, and then it wants to radiate that energy back out to cool off in the infrared. But guess what? The infrared is blocked by the windows. And so what you have inside your car is a miniature greenhouse effect, and your car gets warmer. It's much warmer than it is outside because the infrared radiation can't get out. What do you think? Pardon me? Her seat's still warm too. Yeah, actually, when we set this up, when Erica set this up, I was down here with a cup of coffee, and you could actually see the very dark water too. It's pretty cool. Yeah. Yes, Maria, thank you very much. Oh, I see. Okay, great. I'm going to switch to this one because I'm going to be doing that one in just a second. If you remember the movie The Predator, it's an old movie now. I should ask Maria to talk like Arnold Schwarzenegger. It bleeds. I don't know how to do it. I'm very good. Anyway, the Predator. The Predator was was the evil alien. The Predator could see in infrared. He could see in infrared, so he could spot. They could spot the people he was trying to get in the infrared part of the spectrum. That's our heat signature. So objects radiate in the infrared, and it's a way you can cool off. So if you're hot, humans cool off a lot by sweating because evaporative cooling is really, really efficient. That's what sweating is. But we also radiate, and all warm objects, actually all objects, but warm objects especially radiate, okay? Are there any ideas of something else that might cool itself off by emitting infrared radiation? There's one big thing that really can only cool itself by emitting infrared radiation. Yes? Earth. Earth only has one way to cool itself off, and that's by emitting infrared radiation. It's the only way. Earth can't sweat. Earth can't have convection like a convection oven. That doesn't work because what does Earth touch? It touches the vacuum of outer space. Earth can only cool itself by infrared radiation. So imagine for a second you were putting something around Earth that blocked infrared radiation. And that prevented the Earth from cooling itself off because it's emitting this infrared radiation, but the infrared radiation is not escaping. I just explained the physics of climate change. Seriously, that's the physics of climate change in a nutshell, okay? So when somebody tells you that the Earth is not warming, when we know we have 400 parts ppm, parts per million of CO2 in the atmosphere, which blocks infrared radiation exactly like the car window does, that's the whole physics of climate change. Yes, there are lots of other details about how the Earth might change over time, but I've just explained the physics of climate change. It's, of course, a very important topic, and it's not that complicated. Okay, So I want to talk about the other parts of the spectrum and talk a little bit more about ionizing radiation. Let's see. Sarah's question about microwave ovens, yes? Or microwaves? Cell phones, that's what it was. Thank you. Cell phones actually use the microwave part of the spectrum, which is right here. And so it's pretty far down. It's definitely in the non-ionizing side of the spectrum. And so do microwave ovens. And so microwave ovens, though, they do something very, very special. And I want to show you this. Let's see, I got to change the channel. Channel 8. Okay, so what I've got here is I'm going to put water in one cup, a little bit of water with an ice cube. This is just regular frozen water. So now I've got ice water. And then in another cup, I'm just going to put an ice cube only. And I'm going to put them both in the microwave. And I'm going to put it on quick minute. And while we're waiting for that to cook, I want to talk about another, this is ionizing. We're going to get back to this in just a second. Here's where the cell phone frequency bands are. So they're pretty far down on the spectrum. And so what cell phone frequency bands do, which are actually quite similar to the microwave oven, but the microwave's a little bit special, and I'm going to show you that in just a second, is when it comes to human tissue, they don't break up any bonds. So there's no concern about microwaves damaging DNA. They tend to jiggle molecules around. Jiggling molecules around causes heat, okay? And so, for example, this is the heat map of someone's head, or at least a mock-up of someone's head, who's been talking on the phone for a while. And so what you can see is, around the ear especially, you'll see that it heats up, okay? Now, of course, there are other ways to heat your head up. You can exercise vigorously, you can go out on a hot day. This heating can be localized, and of course, it depends on the intensity of the microwaves. But when you hear people say that cell phones cause brain cancer, what you have to understand is that it doesn't cause cancer by breaking DNA bonds. And the research on whether or not there are other mechanisms that may be heat-related is a bit mixed. But large-scale studies, especially with the high level of use of cell phones, doesn't seem to indicate that there's really anything associated with cell phone usage. Now, it may depend a lot on the intensity. Fortunately, cell phones don't really put out a huge amount of radiation. Microwave's done. We've got hopefully some warm water and what would the ice do? Melt, right? Let's see. So here is the cup. Can we see the beaker? I'll put the beaker down here. This is the cup that had the water plus the ice cube in it. Warm water. No ice, where'd it go? It melted. Now I want the cup that had the ice cube in it. You see that okay? Little bit of water, but the ice cube's still there. The frequency of your microwave oven is set to the perfect frequency that causes liquid water molecules to jiggle very efficiently. Microwaves are ideally trained to heat water, liquid water. So when I put an ice cube in liquid water, it was steamy, it was almost boiling, and the ice cube melted. When I put a solid ice cube, which would require a different frequency in the microwave, that's not the right frequency, it actually doesn't melt very quickly. If you've ever tried to thaw something in your microwave, and then after a few minutes it comes out, and some of it's still frozen and some of it's cooked, what happened was probably the part that began to thaw, the water became liquid, and then it cooks very quickly. And so that part's cooked. The part that's still frozen is not heating up very efficiently. So microwave ovens use a very, very specific part of the microwave spectrum, whereas cell phones use a much wider part. But the idea is the same. Now, the cell phone heating is not so concentrated as the microwave oven, so it's not like your head's going to explode or boil or anything like that, but it will get warmer. Yeah, that's right. The eye is what, 90-something% water, basically, and so microwaves can be very efficient at transferring energy to the eye. So let me talk now a little bit about the ionizing part of the spectrum, because this is where you get more damage, things related to cancer and things like that you might associate with radiation. So, as I mentioned before, ionizing radiation, now this energy, remember we talked about higher energy. This is the higher energy sources of radiation. These can break the chemical bonds, and in particular for human beings, it can damage DNA. And we know that DNA is responsible for how cells replicate. So if the message on how to replicate is now confused or damaged or messed up in some way, then you have the potential for problems. You have the potential for cancers in reproduction. You have the potential for birth defects. And this is what you hear about a lot when it comes to radiation. Yes, Uma? With the what? Yes. Here? Oh, can you kill bacteria with ionizing radiation? Yes, you can. Yes, you can. And in fact, I mentioned earlier, and some of you were specific to my example, would you eat irradiated food? There are places that actually irradiate food with irradiate meat with very specific type of gamma radiation. And the reason for that is to kill some of the bacteria in the meat. And one of the things it does is it prolongs shelf life. That meat is not radioactive, but it has killed the bacteria in the meat. So that's just one example. Please. Thanks. Okay, so could you modify like the bacteria with radiation? I think the answer to that, it's a really interesting question. I think the answer to that is yes. The challenge there is it's not a very well controlled process. So, part of what you'd like to do if you'd like to do some kind of genetic, modeling or something, or do something specific, you'd like to be able to control exactly what you're doing. And usually when you have some source of radiation, it's doing all kinds of different things. So I think the answer is yes, but, and the but is a big deal in that case. Great question, though. Yes. Okay, so obviously this can be bad. I mentioned this. If you have radiation that damages DNA, that's a bad thing. It can be good for things like cancer treatment. I bet everybody in this room knows someone who's undergone radiation therapy for cancer. Some of you yourselves, right? That's a good use of radiation. There are other examples. Let me come back to that in a few minutes. That we use radiation quite commonly to actually kind of make better products, quite honestly. Here's the good news. I mentioned earlier, we're swimming in DNA all the time. DNA. Yes, we are swimming in DNA, but that's not what I was going to say. We're swimming in radiation all the time, and in fact, we're swimming in some ionizing radiation. I'm going to show you in a few minutes that actually cosmic rays from outer space. You also are probably familiar with radon gas. Radon gas is in the environment. There's radiation in, I had my banana earlier, but a banana actually has a fair amount of radiation in it. Fair amount, a tiny amount, I should say tiny. But we have ionizing radiation that we're exposed to all the time. Why don't we all have cancer, or why don't we all have problems? And one of the reasons is, first of all, not every radioactive decay is going to bump into a DNA molecule, for sure. That's definitely true. The other thing is that our system, our reproductive system, our DNA, has an amazing autocorrect system. Much, much better than your iPhone. It's actually able to go through and find essentially genetic mistakes, genetic mutations, which are not all caused by radiation. Genetic mutations happen for a lot of reasons, but in fact, our system has very good autocorrect. So for cells that are actually replicating slowly, our system kind of does autocorrect. For cells that are replicating very quickly, it doesn't have time to turn on, and DNA and radiation will kill those very quickly. That's why radiation therapy for cancer treatment works, is because your exposing tissue to radiation, of course, you'd like to irradiate only the tumor and not any of the good cells, but sometimes you can't avoid irradiating some of the good cells, but those cells are way, way more likely to recover. So the net is a positive, that you're more preferentially going to kill the cancer cells than you are the good tissue because of essentially our autocorrect system, which is really amazing. It really is amazing. So Cancer has an cells with DNA have an autocorrect. The thing is, it doesn't have time to catch it usually because the cancer cells tend to be replicating very quickly. So it's really the timing, the replication rate that makes the difference there. And we've already gone far beyond my expertise with physiology and biology. I'm a physicist. I should stick with electromagnetic radiation, that's for sure. Okay, X-rays are a good example of ionizing radiation that probably everybody's been exposed to. We all have X-rays. Here's an example of Fido apparently swallowed the car keys. Unfortunately, that's not good. But what happens there is the X-rays, remember the X-rays, if you remember the spectrum I showed you earlier, they're way, way over on the right-hand side. So these are high energy. So they are ionizing. X-rays can cause DNA mutations, for example. But the X-rays tend to penetrate tissue very deeply. So most of the X-rays go all the way through. And in fact, what happens is bones or collars or car keys will absorb the radiation. You're looking at a shadow image. That's what that is. That's a radiation shadow image. That's how X-rays work. Now, the amount of radiation you get from an X-ray, you go to the doctor says you need an X-ray, the amount of radiation you get is very small. And in fact, one of the improvements that's happened over the last several decades is because now the sensors are even better, the amount of radiation you need to produce a very clear image like this is really small. So don't worry about getting an X-ray. Getting lots and lots of X-rays, well, it's still a little bit of a dose. It's nothing compared to the kind of thing that you would want to worry about, okay? Radiation dose from one X-ray is really tiny. Ultraviolet radiation is also ionizing. What do we worry about in the summer? We worry about getting too much sun exposure and skin cancer. Okay, so in the electromagnetic spectrum, it's really interesting. Infrared is heat radiation. We saw that with the camera. And then there's the visible. The visible is non-ionizing. There's visible light all over the place. And then just past the visible on the other side is ultraviolet. The low end of ultraviolet is not ionizing. The high end is. Ionizing radiation from the sun in ultraviolet will give you a suntan, but also is potentially damaging DNA, and that's where we potentially can get skin cancer from. Now, I'm not going to get into this for time, but there are actually different parts of the UV spectrum, and sunscreen blocks some of it, et cetera, et cetera. I don't want to get into that, but the point is, this is where skin cancer often, not all skin cancers, but some come from, is the ultraviolet part of the spectrum, okay? Now, more radiation means that your chance of getting cancer or something is higher. And so what this graph is showing you is here's radiation dose. This little box here is for experts, for people who know what a millirem is or a severe, but don't worry about it. It's really not, the detail is here's radiation dose, and here's the excess relative risk of cancer. Now, that's a very funny term that I use there, excess relative risk of cancer. One of the things you have to think about if you're trying to measure whether or not radiation is increasing your chance of cancer is, what are the chances to begin with you might have gotten cancer? Whether it was from just genetics, just from your own kind of family tree, or from other, maybe other exposures in the environment, that kind of thing. So they talk about excess cancers. How many extra cancers would arise from some radiation dose? Now, these data points are primarily from data from the atomic bomb blasts in World War II. That's primarily where this data comes. This spectrum is pretty high on the radiation spectrum. These are high radiations, and you can see these are excess relative risk, so your chances are going up as you get more radiation. Where we live here, humans get, I said over here on this little aside, humans get about 300 millirem a year just from natural sources. That's way, way down. It's even below this little first point here. It's way, way down here on this spectrum. And in fact, we don't know for sure whether this line really works down here or not. Let me just give you one example of why we don't know this. Do you think people in Denver get more radiation or less radiation than we do? More. Why do they get more? They're at higher altitude. That means at higher altitude, there's less atmosphere protecting them from radiation from outer space. And so they get more radiation. Not a lot more, but they get more. Okay? Now, if radiation caused extra cancers, they get more radiation than we do, even though it's a little bit. There's a lot of people, so you can measure this. The cancer rate for people in Denver, or at living at high altitude in general, is actually a little bit lower than it is for people living at sea level. Now, we don't know why. I'm not trying to claim by any stretch that the extra radiation they get is actually helping them. We just don't know that because it's really, really hard to measure compared to everything else. The point is, it's not clear down here on this part of the spectrum whether a little more radiation is bad for you or not. Certainly when you start getting a lot of radiation, more is worse. But on the very low end of the spectrum, where we all are, getting a very tiny doses of radiation a year, it's not clear whether more is bad. Yeah, so that's a really good question, and I don't know the answer to that one. What I completely agree, airline pilots or even people who fly quite a bit certainly get more radiation dose than people who are here on the surface of the Earth. Earth is swimming in radiation from outer space. There are two things that really protect us really well. One is our atmosphere. It really blocks a lot of stuff out. The other is our magnetic field. Our magnetic field causes a lot of charged particles to kind of spin in the spiral in the field, and they never get to the surface of the Earth. So when you're up at higher altitude, you have more of a radiation dose. Really interesting question to know whether or not there's an increased risk of cancer in pilots, and I just don't know the answer to that. For sure they get a larger dose. But again, I'm not talking about 10 times more or 100 times more. I'm talking about 20% more, something like that. And we're already on the low end of the spectrum. Yeah, I want to come back to that because this is an important question. For example, if we want to go to Mars. If we want to go to Mars, we have to get out of the comfort of Earth's atmosphere and Earth's magnetic field. And in fact, one of the biggest challenges to overcome for long-duration spaceflight is radiation exposure. And it's a tough one, because how would you like to shield yourself from radiation? You would love to live in a lead-lined spaceship, okay? But a lead-lined spaceship is not so easy to, get up to very, very high speeds to get you to Mars very efficiently. And so radiation in space is a big concern for long-duration spaceflight. Even, so astronauts who live, I got ahead of myself again, but that's just fine because it's a great question. Astronauts who are on the space station, they still benefit from the Earth's magnetic field. The space station's up about 300 miles, 250. They still benefit from part of the Earth's atmosphere, but a lot less, but they benefit a lot from the Earth's magnetic field, and they get a dose that's something like 20 times more than we get here on Earth. Okay? Now, they're typically up there for a year, so 20 times more over 1 year, it's not like hairs falling out and things like that, but if you're up there for several years, it's a real issue. Yeah? Okay, so Inga says that the 2007 study, she Googled it in real time, and 2007 study says incidence of cancer among stewardesses and pilots is higher than it is for everybody else, which is not a surprise, but I'm sure that's, again, these are not easy things to measure because obviously, again, this excess cancer rate is something you have to measure on top of kind of normal cancers that we get as humans, and especially as we live longer, we're just more likely to get cancer over time. So anyway, I don't want to talk much longer because we're getting short on time. I want to just say a little bit about high-energy radiation. And this is the radioactivity that probably you thought you were going to hear about the whole time anyway. So here's an atom, and inside an atom is a nucleus. And if this nucleus is not stable, then it can emit radiation. And that's the things like alpha radiation and beta and gamma radiation. Here's an example. A uranium nucleus that's unstable will emit something that has 2 protons and 2 neutrons in it, which is actually what we would call a helium nucleus. That's the nucleus of a helium atom. But when the uranium atom, because back when this was discovered, folks didn't realize that was a helium nucleus, they called it an alpha particle. So we call this alpha radiation. And then there's a daughter nucleus left over, that in this case would be thorium. This kind of process happens all the time if you have uranium. And I'll show you this with a Geiger counter in just a second. Here's my question, though. Wait a second. Helium nucleus, that's not scary, right? Balloons, right? Balloons, squeaky voice. If you inhale the helium, your voice squeaks. That's not very scary. So what's the concern here? The concern, again, is the energy that it carries. So this helium nucleus, or this alpha particle, this isn't the car moving at 2 miles an hour. This is the car moving at 60 miles an hour. So it's the energy that it carries that actually is the concern. And I'll show you this with I'll show you the Geiger counter in just a second. But this is another example of a nucleus, a carbon-14 nucleus. We use this for carbon-14 dating. It will emit what's called a beta particle, which folks later on learned. That's what it was named because they didn't know. We called it beta. Give it some Greek letter and we'll figure it out later. That's what happened back in the 1920s. And we figured out later that this thing was an electron. Of course, electrons are all over the place. Electrons are flowing through the wires, causing the lights to light, things like that. So why is this beta radiation? Why is it a concern? Again, it's the energy that this particle's carrying. So as this particle comes screaming out of here, if it runs into something, in particular, like I was saying earlier, if it runs into a DNA bond, that's a problem. And of course, there are lots of these things. Let me just give you a sense of what this looks like with the Geiger counter. And then I want to show you the, let's see, Geiger counter's channel 1. Okay, it's on this side there. And I have to turn it on. That was one click. There's one. There's a couple. Those are just background radiation. So here's the wand. This is just measuring background radiation. I don't radiate, apparently. So let me grab a source here. By the way, when it comes to alpha and beta particles, they tend to not be penetrate very deeply. So your skin and your clothing act as a pretty good protection. The thing you worry about is if you ingest it, because then you don't have that protection. So this is a radioactive source. And we're getting a fair number of decays here. It's not a real hot source. What's going on is those decays are coming into this wand, and then they're ionizing some of the gas, and then that's what we're detecting. So actually, it's just knocking electrons off of a gas, but that's ionizing radiation. When I hold it up here, I'm certainly not detecting any of the microwaves or the infrared, because those are all non-ionizing. This Geiger counter detects ionizing radiation. Yeah? What is the source? Good question. I can't read that. Erica, do you know what this source is? Whoops. It might be americium. That's a common source. It's 1 microcurie of europium. It emits gamma rays. It emits gamma rays, which I didn't talk about, but they actually behave similar to beta radiation, except they tend to be a little bit more penetrating. Okay. But let me show you an example. Oh, let me turn this off because those clicks get annoying very quickly. I want to show you another example of being able to observe radiation. This is called a cloud chamber. It's one of my favorite things. I can just stare at this for hours. So inside this container is a volume of alcohol, and it's actually supersaturated, which means there's a whole bunch of gaseous alcohol. And so what happens is, I mentioned earlier, we're getting radiation from outer space. Atmosphere blocks almost all of it, but a little bit of it makes it, and it hits us for sure. So when that radiation passes through this supersaturated gas, it will ionize, and that ionization in this case causes the alcohol to condense, and it leaves a track behind. So when you see these little lines, you see some of them? Those little lines? Those are not the cosmic rays themselves. Some of them would be protons, some of them would be muons, which are other subatomic particles. Those are the trails left behind. Think of, on a clear day, look up and you'll see a trail, a white trail, a vapor trail. You may not see the airplane, but you're seeing the condensation it left behind as it passed through. That's what you're looking at here. And so this is radiation from outer space. Like I said, most of it is being blocked by our atmosphere, but this is radiation from outer space. And let me see, I'm running a little bit short of time, but let me just do one more thing, and I'll wrap this up. And that is, I want to put a radioactive source in here. Now you see all the extra tracks now? They're kind of horizontal, lots of horizontal lines. That's because this source is spraying a lot of radiation in there, a lot more than you were getting from cosmic rays. And so you're seeing the trails those particles leave behind. I think this is so much fun. We were just talking before the talk that somebody should make an app that's like this, so you can just like stare at your phone, or have a screensaver where you can watch these tracks go by. Because this is back in the old days. This is actually how we did science with trying to measure the properties of subatomic particles. I think this is really cool. Okay, yeah, okay. You can observe. Inga's saying you can observe cloud chamber. You can go online and observe cloud chambers. I knew there was YouTube videos of cloud chamber. I didn't know you could do it in real time. Okay, I gotta wrap up because I don't want to take your whole Saturday. I lost my clicker. Okay, just a couple more things. I already talked about how our atmosphere and our magnetic field protects us. This was a statement, thanks Erica. This was a statement, folks studying long-duration spaceflight. International Space Station astronauts receive a radiation dose that's 27 times higher than we receive on the surface, and it's still protected by the magnetic field. Given our current knowledge, the level of radiation astronauts would encounter would not allow a human crew to undertake a Mars mission. Radiation is a real issue for long-duration space travel because there's lots of radiation out there in space. Okay, so radiation would be sufficient to kill humans in a very long-duration space flight, for sure. Are there other species that could travel in space for a long time? Cockroaches can be exposed to enormous amounts of radiation and be fine. Physiologically, I don't know the details, but certainly there are, cockroaches can be exposed to a lot. So probably the aliens that are going to come look like this one. I'm just kidding. That's just fun. Okay. I want to wrap this up. There's a real interesting website where you can actually estimate your own annual dose. And what's interesting about that is, first of all, you'll see that there are things on there that are kind of interesting, like how many X-rays have you had? And then so you can say, I've had 4. And then you can see how much your dose changes, and you'll see that it changes by not much. There are things like that. But otherwise, I said these things, so I want to keep going. I already talked a little bit about radiation therapy. Now, the way this works for radiation therapy is these radioactive sources we're talking about are materials that have nuclei that are unstable and they decay. And that happens randomly, and it sprays the radiation all over the place. So that's not good for treating cancer. What you want is a really super narrow beam of radiation that you can aim right at the tumor. So you're irradiating the minimum amount of good tissue. And we do this with particle accelerators. About every single hospital in the country has a particle accelerator that looks like this, that produces X-ray radiation that can be focused very, very narrowly and can be really used to target the tumor. And minimally, it certainly damages good tissue, but it minimizes the damage to the good tissue. And so that's the idea behind radiation therapy for cancers. Now, one of the challenges here, this is an electron accelerator to make X-rays. The X-rays don't penetrate your skin very far, so this is very effective for what we call shallow tissue tumors, things that are relatively close to the skin. Okay? This actually shows that this is the radiation dose versus depth, and here's the X-rays. So you get a lot of the X-ray energy deposited within just a couple of centimeters of the surface. So if you have a skin cancer or a tumor that's in shallow tissue, X-rays are good for it. If you have deep tissue cancer, a couple of examples, one would be prostate, another would be brain cancer that's deep tissue. Actually, proton therapy is actually potentially very good because the protons they'll deposit radiation on the way in, but they actually deposit almost all their radiation, the radiation dose, if you will, the energy very deep. Now, the problem is a proton accelerator is a much bigger deal. This is an electron accelerator. Now, this costs a lot of money, don't get me wrong, but a human fits right there. So this is not gigantic. This fits in a room. There's one over at Carl. There's one over at Presence. These are very common. Proton accelerators are a much bigger deal, so there aren't nearly as many of them. There are some up in the Chicago area, for example, but they're not everywhere. But proton therapy is another form of radiation for cancer therapy. Now, this is another kind of particle accelerator. It's a little bit bigger. This is where I do some of my research. This is Fermilab, which is up in the northern suburbs. We're not treating cancer with this one. We're using it to explore the subatomic world. But it's the same technology. This is about a mile around, so the particles are getting up to very high energy. It's the same technology as this. It's just a very, very different energy scale. This is way off to the right on that scale I gave you sooner. Okay. Last thing I wanted to just tell you is other applications for radiation. Computer chips, your iPhone probably has computer chips that had an ion implantation process, which is a low energy radiation process. Car tires, the so-called vulcanization process to make the rubber hard in your tires, used to be done by a very, very nasty chemical process because just real rubber is really gooey and soft, and we don't want tires like that for sure. On a hot day, the tires melt. Some of you who are old enough might remember that that's the way it used to be. Now, they're actually kind of vulcanized with a radiation process because radiation can help polymerize these materials. Diapers, I won't get into this, but diapers are actually can be radiation prep. Shrink wrap, the kind of things used for meat packaging, they're made into the materials, the type of properties we like through a radiation process. Furniture finish, etc. There are some other things going on. I could give you a whole talk about safe nuclear reactors using what's called accelerator-driven systems. That's use a particle accelerator to turn on and off the reaction. It's really interesting technology, and folks are pursuing it in different parts of the world. Things like stronger concrete. This gets back to the whole polymerization process. Now, don't worry about this. These things are irradiated, but that doesn't mean there's any residual radioactivity. So your cell phone doesn't have the computer chips in your cell phones do not have residual radioactivity, but particle accelerators are used to irradiate these things to make them what they are. Worldwide, there are more than 30,000 particle accelerators in use, and almost none of them are used for science. I mean, I go to a particle accelerator to do science, but there are only half a dozen or maybe 10 or something like that used for science. The other ones are in hospitals everywhere, and they're in manufacturing facilities and things like that. And so radiation is used ubiquitously to produce a lot of the products that make our life the way it is. So, just to circle back to where we started, radiation is both good and bad. It depends on the type of radiation. It depends on what's going on with it, how it's used. Of course, we want to be careful. There are situations where radiation can be very dangerous. As I mentioned before, in 2 weeks, Matthias is going to be talking about nuclear proliferation and things like that. That's, of course, an example where radiation can be extremely dangerous. There are a lot of things to be concerned about. As you go through your everyday life, radiation shouldn't be high on your list. My example, when I talk to my students, we were talking earlier about cell phones. I said, don't worry about cell phones and brain cancer. Worry about cell phones and driving. That's way, way more dangerous than radiation risk from cell phones. Okay, thanks very much, everybody. The question is, what makes fallout radioactive? So when you have an atomic bomb that explodes, so you have, what happens is you have either uranium or plutonium that is fissioning, which means those nuclei are splitting apart. And they split apart a lot of different ways. And once they split apart, they release a huge amount of energy, and that's why atomic bombs are so powerful. But you're still left over with all those secondary particles. And many of them are unstable, which means they're going to be spitting out alpha radiation and gamma radiation and beta radiation. And some of them are going to be around for tens of thousands of years. And there are lots and lots of them. I mean, we're talking about billions of particles, things like that. So the fallout can be extremely dangerous. And you have fallout range. You know, couple examples where we've had not atomic bomb detonations in recent history, but Fukushima, which was the nuclear power plant in Japan. Around the power plant, there was residual radiation, which is effectively, we don't use the term fallout for that, but that's effectively what it was. Yeah, so a couple really good questions there. So first one on microwaves, is there any residual effects there? The answer is no. The answer is no. Microwaves are, as I mentioned before, microwaves are jiggling water molecules very efficiently to heat up the water, but there's no residual radiation. Not in the food. There's no radiation in the food. The one thing you have to, actually it's not nearly an issue as it used to be. A lot of restaurants would have the microwave in use. Be careful with a pacemaker, and that's because the microwaves might disrupt the pacemaker. That's not such a problem anymore because the microwaves are much better shielded now, so the microwave radiation really doesn't get out. That's not even an issue. So no concerns, absolutely none. I will eat microwave popcorn forever and not have a single worry about it. And then you asked about MRIs and CAT scans. So CAT scans are X-rays done all around in different angles. So you're getting a lot of X-rays at once. So you do get more of a radiation dose. But again, the trade-off between the benefits of the diagnosis and potential treatment for whatever else you're trying to find with a CAT scan versus the tiny, tiny, super tiny extra radiation dose is a good thing. MRIs actually operate a very, very different way, and they actually look at how hydrogen is jiggled in your body and how it radiates, and so that is actually in the non-ionizing sector, so that you don't have to worry about it all. You get as many MRIs as you want, you're safe.
Let's just have one last question. Global warming, does the increased general temperature increase the potential damaging effects of radiation?
So the increase in temperature affect radiation. I don't think so. However, there are some things that do. One of the things that's really important, actually, we've recovered from somewhat, is the depletion of the ozone layer. Because the ozone layer, which is in the upper atmosphere, ozone is O3. Oxygen we're breathing is O2. Ozone's O3. Ozone's extremely efficient at blocking UV radiation. I kind of blasted past that in my talk, but a lot of the ultraviolet radiation from the sun, which would be cancer-causing, is actually blocked from our ozone layer. About 30 years ago, we were doing quite a job at depleting our ozone layer, but we actually took action and it has recovered. And it's actually a success story of science informing public policy, and wouldn't we love it if that could happen more often? I'm happy to talk to folks down front if you want to come down and have more questions. Thanks a lot.